Hello everyone, welcome to Jigyasa's video tutorial series on BWSim-5G simulator. In this video, we will be delving deep into the concepts of beamforming in advanced antenna systems. So, what is beamforming? For that, you need to understand following use case. Consider a bustling urban cityscape with dynamic user movement and the presence of numerous structural challenges. Traditional wireless systems can face these hurdles such as signal obstruction and interference. Users navigate through crowded street facing signal degradation and connectivity issues. Enter beamforming, which optimizes the connectivity and transforms the urban wireless systems. What is beamforming exactly? At its core, it's an advanced signal processing technique that dynamically tailors the direction of the transmitted signal. Imagine antennas behaving like precision instruments. That is, you are precisely being able to focus the radio RF energy exactly where it's needed. By manipulating the phase and amplitude of signals across an array of antennas, beamforming concentrates energy into specific beams, thereby its name beamforming. So, what is the result? Enhanced signal strength, minimized interference, and optimized connectivity. This makes it quite an essential tool in wireless communication toolkit. Now that we have an idea of what beamforming is and where exactly beamforming is used, we are going to perform certain experiments, simulations, to see the performance of these advanced antenna systems when we change the number of RF chains, the number of antennas, and the bandwidth, and make certain inferences on how the advanced antenna system behaves in these cases. Let's move into the experiment. So let us start with the first phase of the experiment. Now what we are going to use is check out the network throughput performance for three different number of RF chains. They are 32, 8 and 2. And the parameter in question, throughput, can be arrived from the system level simulation. Therefore, we have to perform a system level simulation. This can be performed by unchecking this option under simulation configuration called as is for calibration. Now that the configuration necessary for running with the number of 32 RF chain is over, let us actually run the simulation. Okay, now that the necessary simulations are completed, let's take a look into the throughput performance of these three RF chains. We filter on the CDFs alone, RF chains. Is the regular rational thinking is when you increase the number of RF chains, you expect that to be an increase in the throughput. If you can see here, number of RF chains when equal to 32 is clearly outperformed by both the number of RF chains when equal to 8 and number of RF chains equal to 2. So there is something that causes the deviation from the usual rational line of thinking. That is where we have to understand that while we change the number of RF chains, we made the number of antennas to remain the same. So what exactly is happening is we reduce the ability of the antennas to give a strong beam that is traveling the entire way it was intended to travel, thereby causing this issue. Say, if you have a larger number of antennas checked it for 32, 8 and 2, you would get a result which resembles the rational line of thought that was discussed earlier. Now that this phase is over, let us move on to the next one, where for a constant number of RF chains, we'll be checking out three different number of antennas. Okay, now we have completed the simulations and let us take into the look what role does the number of antennas play when we keep the number of RF chains constant. Let me move to the parameter in question, which is the throughput. And then let us also filter out the CDFs alone. Oh, what can be seen here is as the number of antennas increase, the throughput performance also increases. Remember the rational line of thought we had when we discussed the first phase of this experiment? That comes over here. That is where this is proven. Higher the number of antennas, better the network performance. Multiple antennas enable what is called as spatial multiplexing, where multiple data streams can be transmitted simultaneously over the same frequency band. This results in an increase in the overall data rate, enhancing throughput. More antennas provide additional spatial dimension, increasing the overall channel capacity. This allows for a higher number of independent communication channels, leading to improved data throughput. Despite this being quite an obvious line of thought, I wanted to show you that when you increase the number of antennas for a constant number of RF chains, the network performance improves. Okay, now that we have completed the simulations, let us look into the role the beamwidth plays in the SAR performance. Take a look into this graph. As we reduce the beamwidth, the SAR performance deteriorates. But this shouldn't be the case, right? A narrower beamwidth has the potential to improve SAR by focusing the transmitted energy. But along with it comes the need for beam sweeping to cover the entire cell, which introduces challenges related to temporal variations and interference during the beam switching adds complexity to system. While narrow beams are advantageous for focus communication, they inherently cover a limited area. To provide comprehensive coverage within the entire urban cell, beam sweeping is necessary. Beam sweeping essentially involves dynamically adjusting the direction of the antennas to cover different sectors of the cell. And this is why, in this case, when we reduce the beam width rather than following the expected thought process of better SANR performance, we get a deteriorating SANR performance. Now that we have had several simulations to understand and interpret the behavior of advanced antenna system using the system level simulation, I hope you have an idea of beamforming. For any doubts regarding implementation, you can contact the Jigyasa team. I will meet you again in another video with another wireless concept. Thank you.